So in this question, we're going to find the eigenvalues and the eigenvectors for this linear transformation. Now, we've got some transformation t, which is in 2 dimensions. And t is given as x and y is 6x plus 3y and 2x plus 7y. So our end goal is to get the eigenvectors as well as the eigenvalues. So how are we going to go about that? Well, first step, the easiest way is to turn this into matrices representation. So let's do that. So let's represent this as some matrix A. So then that would be, so lining up my x's, I've got a 6 and a 2. So I'll put them in the vertical parts. And then the y's are 3 and 7. So I'll set that up as my matrix A. Right, okay. So now first step is to find the eigenvalues. So what we do is we set some characteristic equation. And what we want is determinant of A minus lambda times the identity matrix, set that to be 0. Now let's break this apart, this statement here. So the determinant of a matrix, we'll go through that in a moment. And lambda is just some scalar constant, and I is the identity matrix. So first of all, the determinant. So the determinant of any 2 by 2 matrix, so the determinant, let's say we've got A, B, C, D as our components for our matrix. So the determinant is A times D minus B times C. And that's how we calculate the matrix, the determinant of a matrix. Now lambda is just a scalar constant, that's fine, that can be just any real number. And I is the identity matrix. So I of a 2 by 2 matrix, that will be 1, 0, 0, 1, where 1 is the value of the diagonals. Okay, so let's go through that. So let's work on this characteristic equation. So we want the determinant of A minus lambda times I. So if I write in A first, so A is 6, 3, 2, 7. And subtract that from lambda times our identity matrix. That's 1, 0, 0, 1, and set that to 0. Okay. Now, first of all, it's a bit like big maths. Let's work the multiplication bit first. So next line of working, we can write, so we want the determinant. Actually, we should technically have a big bracket around all of that because we want the determinant of the whole thing. So determinant, let's keep the bracket. So we've got 6, 3, 2, 7, that will stay. And then multiply all of these by lambda. So then we will have lambda times 1 is lambda, 0, 0, and lambda. Okay, and that is still set to 0. Okay, now we can just subtract these 2 matrices. So next line we'll have the determinant of 6, 3, 2, 7 minus lambda 0, 0, lambda. So that will give us, so I can now get rid of this bracket because we're left with our final matrix. So now we'll have 6 minus lambda, 3 minus 0, gives us 3, 2 minus 0, which gives us 2, and 7 minus lambda gives this bottom diagonal. Okay, and we still set that to be 0. Okay. Now we've got our formula for our determinant, which is AD minus BC. So A times D. So that's our A and our D component. So now our determinant now will be 6 minus lambda multiplied by 7 minus lambda. And then subtract B times C. So minus 2 times 3 or 3 times 2, either or. I'm going to write it as 3 times 2. And that is 0. Okay, so now we're going to end up with some kind of quadratic where we multiply this out. So I've got minus lambda times minus lambda, let's put that first. So that's lambda squared. 7 times minus lambda is minus 7 lambda, and this one times this 6 is minus 6 lambda, so minus 7 minus 6, minus 13 lambda. 7 sixes are 42, so let's write that as plus 42 and minus 6, and then that is 0. Okay, right, let's just continue just over here just to finish off and solve for lambda. That's our next goal, and that will give us our eigenvalues. So now I've got lambda squared minus 13 lambda, and then plus 42 minus 6 is plus 36, and that's still 0. Okay, right, so now let's try and solve for lambda. Now I've got 13 here as the difference between my factors of 36, which is quite handy because I know 9 and 4 are factors of 36. So therefore that's going to leave me with lambda minus 9, lambda minus 4 equals 0. So I'm happy with that as my factoring of this quadratic. So solving for this, my two eigenvalues then will be lambda minus 9 equals 0. So that will give me lambda equals 9. So straight away I can put that in there. And my other one, lambda minus 4 equals 0. So straight away I can also say lambda equals 4. So we're well on the way now to finding our eigenvectors. So what I'm going to do now is clear this off the board, and then we go through finding our different eigenvectors. Okay, so let's find the eigenvectors. So now for the eigenvectors, we want the next equation, which is A minus lambda I, which is the identity matrix, which is what we just worked out previously, times our standard vectors x and y, set that to 0, and then we solve. So it's a little bit similar to this one, but not the determinant. Now we worked out this one previously, which is from this one, and this part, that gave us 6 minus lambda and 3, and 2 and 7 minus lambda. So that's our A minus lambda I, and our standard vectors, that's just x and y. So that's x and y, and that equals 0. Okay, so now this is how we can produce our x and our y. So now we just multiply these two vectors together. We've got a 2 by 2 and a 2 by 1 here, so it's valid to multiply together. So now I've got 6 minus lambda x and 3 times y. So I add 3 times y, and that is 0. And let's work with the bottom line, 2 times x and 7 minus lambda times y. So add 7 minus lambda times y, and that is 0. Okay, so now what we do is we work out the result of this using the individual eigenvalues. So first of all, let's use lambda equals 9. So let's look for that. Lambda equals 9. So what we do now, we plug in 9 to these equations, and then we see what solutions we get. So 6 minus 9 gives us minus 3. So now I've got minus 3x plus 3y equals 0. And we should get something similar with this one, because this one we get here 3y equals 3x. So it gives us 3y equals 3x. Okay. Now plugging 9 into here, we should get 2x plus minus 2y. So 2x minus 2y. And that equals 0. So that will give us 2x equals 2y. And to keep it the same pattern as this one, 2y equals 2x. So therefore x equals y. So therefore we can, our value for our eigenvectors for the first one of these would be k and k, as x and y are the same value. So that's our first result, k and k, where k is just some constant. K is not 0. So k is not 0. We can take any other real value. Okay, now let's try it for lambda equals 4. So let's take this one off the board and do that. Okay, lambda equals 4. So now for lambda equals 4, let's plug in 4 into these two equations. So 6 minus 4 is 2. So I get 2x plus 3y equals 0. So therefore I get 2x equals minus 3y. Okay, now we should get something similar on this one because we've got 2x here. So 2x and 7 minus 4 is 3. So we get exactly the same equation. So nothing more to do, we've got that already. So therefore our eigenvector when lambda equals 4, that will give us, the next one will be minus 3k and 2. So minus 3k and 2k. And they're specific for lambda equals 9, lambda equals 4. So that's for lambda equals 9. And this one here for lambda equals 4. Okay, and there are eigenvalues and our eigenvectors for this linear transformation. Okay.